In this video, I'm going to show how you can use CAD software to simulate a spirograph. For those of you unfamiliar with what a spirograph is, there's a Wikipedia entry about it. There's people that have done YouTube channels around making spirograph designs, and you can see how these are kind of the interesting, very mathematical, intricate designs that can be made with a spirograph. And then animation over here that shows the general mechanism. You have an interior gear or sprocket and this exterior wheel with corresponding teeth. And you put your pen in this gear, and as you move the gear around, it creates this interesting mathematically shaped pattern. They're a lot of fun to use. As a kid, I would always get frustrated because you'd get partway through one of these designs and the gear would slip off the teeth and you would ruin things, which is where CAD can actually be a fascinating alternative to the real world. And so we'll wait for Rhino to open. And then we'll just start with the standard template, small objects inches. That gives a little bit more absolute tolerance. And we'll be doing a lot of traditional modeling, so we'll move the layers away. We'll move this over here. Oh, actually, we'll move it so that it comes here. And then we'll also open Grasshopper, because what we're doing today will be mostly involving Grasshopper. We'll take this and move it over to this side. Okay, so the first thing we're going to do is we need to simulate the outer wheel with teeth, and so we're going to do that with just a curve. And over here we'll make a circle. Doesn't really matter how big, and we'll set this one to this circle. Great, so that's that circle. And then we of course also need an inner wheel. And again, it doesn't matter how big. And then with that, and then so that we can see outer wheel, and then this is the inner wheel. So the next thing we're going to do is, in order to simulate the teeth, rather than trying to do like a real physics simulation of teeth mashing against each other and all of that complexity, all we're going to do is we're just going to divide this wheel into a certain number of segments, and then mathematically make the software make sure that it always realigns on those segments. So on the big wheel, we'll say that we have 60 teeth. And if you're following along in Rhino, there are several divide algorithms. So you'll see divide by distance, divide by length, and we just want the one that says divide. It's also more precisely labeled divide curve. And then we need to do the same with the inner wheel, except for this one we'll start off with 40. I'll do another video later to talk about how you can choose these numbers and play around with this, but for the moment this will be a good place to start. Now that we have all of these, the next thing that we can do is, so what we're trying to get to is an orient. And what this will do is it'll take some geometry and it'll orient it from one plane into another plane. And so what we need is a start plane and a finish plane. The start plane would be one of these teeth on the inner wheel, and the finish plane would be one of these teeth on the outer wheel. But we don't have a plane that we can refer to. What we do have, though, are points that are represented by all of these dots, and we have tangents at the points. And that actually ends up being enough for us to create a plane. Well, that's not what I need. I need the rotate vector. So what we're going to do is we're going to take this tangent vector, and we're going to rotate at 90 degrees, or 0.5 pi, around the z-axis, which in this view is coming out of the screen. But it's handy because we're working in 2 dimensions. Sometimes figuring out an axis for a vector rotation can be tricky, but in this case it's really simple. So now if we call this the x vector and this the y vector, and this is the origin, we now have everything we need in order to construct a plane. Open up. There we go. So we can take the origin and the x vector and the y vector, and now we have all the things that we need to construct a plane at every point on the inner wheel. Now, some of these things are we're not going to fiddle with this in these exercises, so we'll just internalize that data so that we can clean this up. And then we can actually just copy this up here. And then now we have also all the planes on the outer circle. And since having all these planes visible is impossible to see anything. So the last thing we're going to do, just to be able to kind of visually understand what it is that we're doing, what we want to do is I'm going to show you quickly how the simulation works, but then we'll automate it so that the process goes much faster. So we want a list item, and we want this on wrap, and we need 2 because we have to pull 1 plane off here and 1 plane off here. And then what we're going to do, we're going to say get an integer. We won't need that many, but it'll work. We'll just take the same one. And because this automatically sets to wrap, as we move through here and we cycle through all the points, it'll just automatically circle back to the next one. So and actually the inner wheel is the start plane and the outer wheel is the plane. And then so that we can actually see things moving. So we'll move this geometry, but we'll also move these points. We don't need to see those planes. So you can see how just already it's reoriented this curve from 1 point on, and I guess we'll make these visible so that it aligns on that. And then as we go in, and if we go to the next one, you can see how it, and it just rolls along, just like as if those were gears. But you'll notice something, that one of the things that makes it look weird is the space between these teeth isn't the same on the inner wheel and the outer wheel. So let's go back and let's fix that. So let's go ahead and scale this curve, and since we're centered about the origin, we won't worry about that. And we'll just create something like this, although we'll set it to 1. And then we'll go down here, and we'll also add a scaling factor in here. And then this is what will go to here. Now, the actual length itself isn't what matters in this exercise. What matters is the distance between these 2 dots and the distance between these 2 dots. And so now what we can do is we can take the length of the curve. Because these are circles, we could calculate this right now, but in a later video, we'll want to be able to use different types of curves. And so we're going to build this to start with so that it doesn't depend on the formulas for a circle. So now that we have the length of that curve, we'll just do an expression of x divided by y, where x is the length divided by the number of teeth. And this should show us the number of teeth. There we go. So this should show us something. Okay. And then down here, we need the same thing, except we want it to be divided by these teeth. We're getting a little bit crowded here, so let's go ahead and give us some space. Okay, so now that we have these numbers, the next thing we're going to do is we're going to create an expression, and we're just going to do x minus y, like that. And then, so this number we want to see. And so what we're going to want to do, And we're going to right click here, right click right here. It's on this side. Here we go. Wire display, we want it hidden. So we're actually going to move this around, and we'll always end up sizing the outer wheel. So we'll just move this over here. And what we want to do is we want to size the outer wheel until it's close to 0. And that's all we're really trying to do here, is we just want the outer wheel close to 0. So now as we go back over here and we process our simulation, right, you get a lot more of the effect of it actually rolling along in what looks like what's physically compatible and similar. So this is the basics of, oh, there's one more thing we need. We need a point. Because there's the point in the inner wheel where, so let's set a point. And we'll set it just on the y-axis up here at one point, right there. And then what we'll want to do is we'll want to have this point move along with the inner wheel in the simulation. See, so you can see it right there, and then as we go back in here, you can see how that point, as it goes, it starts to draw out this path that we're trying to make. So you can see how the simulation working. So you could advance it one step, insert a point, advance it one step, insert a point, advance it one step, insert a point, and then manually go and connect all those points. But if we're going to automate this much, we should automate that last step too. So let's go ahead and get rid of this, and we won't need these anymore. We won't need this, but we will need this point, and we'll need the planes. And we're going to create a C# script. And we're going to call this SpiroScript. And I like the script parasite function because it allows me to use Visual Studio Code to do my scripting. And so we'll group these as part of making script parasite work. And then we will go in and let's create our variables. So we're going to need the outside loop planes. And that is a list of planes. And then we need the inside loop planes, or the inside curve planes. And that is a list of planes. And then we need the drawing point. And that is a single item, that is a point. And then the last thing we need is a number. And this is the number of iterations, and this is just an integer. And all we're going to be trying to do with this is tell it how many times it needs to step through, because if we don't give it this number, it won't know. Does it step once? Does it step a million times? It won't know. And to start with, so the outside planes, right? So outside wheel is these top planes. We have that data already. We have this data already. We have the draw point. And then for these iterations, we are just going to take the multiple of the number of teeth on the inner wheel times the number of teeth on the outer wheel, and we're going to multiply those together. And that will ultimately be sufficient. It'll overdetermine the curve, but in another video, we'll do some cool math to be able to be a lot more precise with this. So we're going to have to draw 2,400 points with this mechanism, but this will be enough so that we can get the process started and get the curve drawing. All right, so I started a script parasite. We'll open up a terminal. And then VS Code. And sure enough, here's the Spiro script. And here are my parameters. All right, so the first thing we need to do is we need to create a list of points that will be the curve that we generate as we go through this. So we'll just call this points, and it's a new list. And then we're gonna just iterate, except we're gonna use this iteration parameter that we're passing in. And this computer feels like it knows better than me. We'll get rid of this. And there we go. So this is the iteration. And all we're going to do is, the first thing we're going to do is we're going to create a temp point. And it'll be equal to a point 3D. And what we're going to do is take the drawing point. And we're going to make that equal to the temp point. And then, so that's the pen, and we're going to make it a temp because as we go through here, we're going to want to iterate off of the original point over and over again. We don't want to apply these transformations successively. We want to apply each transformation to the original point. And so because of that, we'll create a temp to make sure that we don't end up moving the original draw point from its original position. So then we'll create a transform, plane to plane, and it's going to be from the inside plane. And we're actually going to do, remember, one of the things that happened automatically when we used the list item function is it automatically wrapped the number of points as we were going to run over it. And so we have to simulate that. And the way we're going to do that is we're just going to take the modulus of I based on the count like that. And then we need the next plane, which is going to be I, but in relation to that modulus of the outside plane like that. And then we have the transform. And then we will apply the transformation to it. And then once that transformation is applied, we will go ahead and add that temp point to our list. And then we will simply take all those points when we are done and put that out as output. So if we hit save and we come back over here, and there is our curve. That is what we are trying to do, just like that. Now, so even though this is pretty handy and you can see what we're doing, I do think it looks better as a curve, not as a sea of points. So we will do an interpolate curve function. We'll just drop this in, and then we'll also bring, because it's going to ask here if it's periodic, and we do want it to be periodic, that way it closes. We can get rid of that, and it looks just like that. And then we can move this point around, and it'll recalculate the draw point, depending on where we put it, just like this. And the one thing we'll do, just at the end of this video, is, so if we look back on the Wikipedia page, and if you come in here and you see this curve, you'll see it's got all of these overlapping lines. And you might wonder how we do that. And the way we're going to do that is we just need to add more draw points. So we'll do a linear array, and we want it to go, don't need that, don't need that either, in the y direction, but we want it to be going in the negative y direction, and this will just allow us to scale the spacing. This up like this. And then we also will need a number, we'll say 6 for the moment. And we'll go ahead and move these so they're all, right, so if this is the inner curve and this is the center, we'll want them like that. And then we'll just put this in to the draw point, and it'll calculate all 6 at once. And that is how we get that curve. And now if we wanted 7, but we wanted them, we can pull them out so they maybe get something like that. So that is how you do it. Now, one of the things you can do is you can come back here from the beginning, and now you can just pick a different number of teeth on the outer wheel, and it will start to create all sorts of different processes. The one thing that we'll want to do is we'll want to always come back and try to make this as close to 0 as we can, so that the patterns make sense from a Spirograph perspective. In a later video, we'll play with doing some things that are physically impossible with a Spirograph, but the first step is to try to actually replicate what is physically done with the toy, and we'll do more experimentation later. Thank you for watching, and I hope you come back for the next video in the series.